All right, well, we talked about how when we have an organic compound and we subject it to a strong magnetic field and then we hit it with all the relevant frequencies of electromagnetic radiation, which are in the radio frequency range that cause resonance or an alpha to beta spin flip. What happens when those nuclei that are flipped from alpha to beta, they relax back down from beta to alpha, and that releases energy. But the amount of energy that gets released is going to differ based on the type of electronic environment that the nucleus is in, right? Because we said that the amount of the externally applied magnetic field that a nucleus experiences is related to the electronic environment of that nucleus, right? If we have more electron density around the nucleus, it's going to be more shielded and it's going to feel less of the electron environment. Whereas if it's deshielded, if it has less electron density around it, it's going to feel more of the magnetic field, the externally applied magnetic field. And so again, the whole point is that the difference of the electronic environment of each nucleus allows us to distinguish between each nucleus in an organic molecule, whether it be a proton or a carbon nucleus. And so the number of signals in a proton NMR spectrum, I'm just reading off the slide, indicates the number of different kinds of protons in a compound. Notice that it says different kinds of protons because if protons are the same, right, that means they're going to be in the same electronic environment. They're going to feel the same amount of the externally applied magnetic field. They're going to have the same difference in energy between the alpha and beta spin state, and they're going to release the same amount of energy. And so we can't distinguish between different types of protons. Okay, so when we have identical protons, we say that they are chemically equivalent. So identical protons, we say they're chemically equivalent, and you're going to hear me say that quite a bit. Now, there's two types of protons that fall under the umbrella of being chemically equivalent. We can have protons that are what are called homotopic or protons that are enantiotopic. Now, first we're going to look at what constitutes a homotopic proton, and then we'll talk about what enantiotopic protons are. So first of all, a homotopic proton. If a molecule has an axis of rotational symmetry, if you can just spin the molecule around somehow, you rotate it around an axis, right, 180 degrees, okay, and it allows one proton to be rotated onto another, well, then the protons are homotopic. That means they're chemically equivalent, okay? That means they're going to show up in the exact same place on an NMR spectrum. We will not be able to differentiate between them. So here's an example right here, okay? So this is isobutylene, but you can see that these two protons are homotopic because if I rotate this 180 degrees, okay, both of those protons end up in the same place and I would not be able to distinguish between them. Right, same thing with this molecule here. This is difluoromethane. If you were to rotate this 180 degrees, close your eyes and open them again, you would not be able to tell which proton is where. Okay, again, they're homotopic. And the same thing with these two protons of cyclopropane. If we were to rotate the molecule around this axis, okay, we would not be able to distinguish between those two protons. Therefore, they are homotopic. They are chemically equivalent. Okay, they're going to produce the exact same signal in the NMR spectrum. So you've got to be able to recognize homotopic protons. If you're finding it difficult to recognize, where is the axis of rotational symmetry in my molecule, there is a very quick test that you can do to determine whether protons are homotopic or not. We call it the replacement test. All you do is replace one of the atoms. So we'll just choose one of them at random and we'll replace this one. Replace it with the deuterium. Now you could replace it with anything. You can replace it with the letter X if you want, but you do the replacement test for both of the protons. So you do it for the first one, then you do it for the second one. And if you end up with two molecules when you've done the replacement test and they're the same, you've done both replacement tests and you end up with the same compound, well, then the protons are identical. They're homotopic. Okay? So homotopic protons, we can identify doing the replacement test if the same compound is produced when we do the replacement test. Okay, so those kind of protons are identical. And then we also can have what are called enantiotopic protons, which are also identical. Okay, now how do we identify protons as being enantiotopic? What we look for now is not an axis of rotation. We look for a plane, a mirror plane of reflection, of symmetry. Okay, so it's kind of difficult to illustrate with just a 2D structure, but you can imagine, if I was to twist, rotate this whole molecule, rotate it a bit more this way, what you would actually see if you were looking down, it would be more like this. You have the carbon, these two hydrogens, and then you'd have the fluorine here, okay? And the chlorine is actually right behind it, okay? So it really, what you would see is the fluorine, and then the chlorine is right behind it, okay? It's not the greatest drawing in the world, but you can see that there is an axis of reflectional symmetry here. And so these two protons are equivalent, okay? They're not homotopic, they're enantiotopic, but they're chemically equivalent, and they would produce a signal that would be identical. The same thing here with this molecule. Again, it's kind of difficult to illustrate it, but there is a plane of symmetry running through the molecule. Give me a thumbs up if you can see the plane of symmetry with these two molecules, or you follow me even partially on the idea of the plane of symmetry, the plane of reflectional symmetry, and we know that the protons are chemically equivalent. Okay, cool, great. Even if you don't follow me all the way, there is a quick test that you can do to determine whether protons are enantiotopic or not. It's the same old replacement test, okay? You do it again, okay? You replace one proton with a deuterium, and then you replace the other proton with a deuterium. Again, it doesn't have to be deuterium, but whatever. A deuterium will work, okay? So if you can't see that axis, again, all you have to do is do the replacement test. And if you end up with two compounds that are enantiomers, then they're enantiotopic, okay? They're chemically equivalent. So if we go back to this one here, right, if somebody says they can't see this, look, if we do the replacement test, if we draw this compound where we have a hydrogen here and a deuterium here, okay? And then we draw the other compound where we replace the other one. So we have the deuterium over here, and we have the hydrogen. We have the hydrogen over here. Okay, what did we do? Okay, all we did was flip the stereocenter, right? And one of them, the deuterium is going up, and the other one, the deuterium is going down. So what's the relationship between these two compounds? They're enantiomers, right? These are enantiomers, enantiomers. So if the two compounds are enantiomers, that means that the two protons are enantiotopic, okay? And it means that they're chemically equivalent. So all you've got to do is the replacement test if you're stuck, okay? I do the replacement test all the time. I mean, the more familiar that you get with, identifying planes of symmetry, the easier it gets. But if you're having difficulty with it, you just do the replacement test. So there you go. So what have we learned so far in section 15.4? You want to determine if protons are equivalent. The first thing you do is look for an axis of rotational symmetry, okay? Where's my highlighter? If you have an axis of rotational symmetry, the protons are homotopic. They're chemically equivalent. If you don't have an axis of rotational symmetry, but you do have a plane of symmetry, then your protons are enantiotopic and they're chemically equivalent. Again, to determine whether the protons are homotopic or enantiotopic, you can do the replacement test. If you end up with the exact same compound, they're homotopic. If you do the replacement test and they're enantiomers, they're enantiotopic, okay? And if you don't have an axis of rotational symmetry, you don't have a plane of symmetry, you got neither of those, then they're not chemically equivalent. And you can still do the replacement test. If you do the replacement test here and you don't end up with enantiomers or the same compound, then they're not chemically equivalent. Simple as that. So that's what we have to look for. So let's say you did the replacement test on these two protons that I have highlighted in green. What do you end up with in this case? You don't end up with the same compound, obviously. You don't end up with enantiomers because this stereocenter is inverted, but this stereocenter hasn't changed. So what's the relationship? These two compounds are diastereomers. Therefore, we say that the protons are diastereotopic. They're not homotopic. They're not enantiotopic. Therefore, they're not chemically equivalent. So whenever we do the replacement test and we end up with diastereomers, the protons, again, are diastereotopic and they are not chemically equivalent. So what have we covered so far? We've covered homotopic and enantiotopic. Those protons are chemically equivalent. And now we've covered diastereotopic. Diastereotopic protons, if you do the replacement test, you don't end up with the same compound. You don't end up with enantiomers. Therefore, they are not chemically equivalent. Take a look at these protons here, okay? The two protons that are highlighted in this, this stereoisomer of 2-butanol, okay? If I do the rotational, right? If I try to rotate this molecule, there is no way that I could rotate this molecule that I end up with the same molecule, okay? So therefore, there is no rotational symmetry. There's no reflectional symmetry in this molecule as well. Now, if you're unsure, what would you do? You could do the replacement test. If I replace one of these protons with the deuterium, so I'll do that now, my hydroxyl stays up. I replace this one with the deuterium. This one is a hydrogen. Then I do the same thing here. I have my hydroxyl, still goes up. Okay, but now I have my deuterium in the back and I have my hydrogen out front. Well, what's the relationship? I have two stereocenters that are the same, but then I have the two stereocenters that are different. These are diastereomers. Therefore, again, these two protons are not chemically equivalent. There's no rotational symmetry. There's no reflectional symmetry. Therefore, they are diastereotopic and they are not chemically equivalent. Now, if you're the kind of person who likes shortcuts, which is, I think, everybody likes shortcuts. There are some shortcuts to help you identify how many signals you would see in a proton NMR spectrum. Let's say you have a methylene, right? Methylenes show up all the time in organic compounds. There's one right here, okay? If the two protons in a methylene and a CH2 are going to be chemically equivalent if there's no chiral centers in the molecule. Look at this molecule. There's no chiral centers in here. There is no stereocenter at all in that molecule. Therefore, this is just a rule. These two protons are going to be chemically equivalent. And if you're like, well, Mr. Dion, there's no stereocenters, does that mean that these two protons in blue would be chemically equivalent? Heck yeah. Does it mean that these two protons in red, would these be chemically equivalent? Again, it's a methylene and there's no stereocenters. So yes, those two protons in green or in blue or in red, they're all chemically equivalent. All right. Now, what else? The second part of the shortcut is this. If you have a methylene, a CH2, that's what a methylene is, okay? They are not chemically equivalent if there's a chirality center in the molecule, done, okay? Since we have a chiral center right here in the molecule, it's this carbon is a chiral center, that by definition renders these two protons non-equivalent. You know, another way that I like to imagine it, and I told you this in the stereochemistry chapter, imagine yourself standing here, okay? What would you see? You would see the hydroxyl pointing way down, right? Whereas if you were to move yourself over, you know, if you were on this proton, what would you see? Then you'd be closer to that hydroxyl, wouldn't you? Right? So you're in a different environment. So you can do a replacement test or you can just pretend you're standing there, right? Anyhow, also, if you were to take this molecule and do the replacement test, you would clearly see that you would end up with diastereomers. However, the shortcut is a lot faster. So two protons in a methylene with no stereocenter, they're equivalent. Two protons on a methylene, when you've got one stereocenter, they are by definition not chemically equivalent. So again, everybody loves shortcuts, but you can see how this already what we've learned in section 15.4 lends itself to, you know, questions very easily, right? Now, if you have three protons in a methyl group, okay, we see CH3s, right? A methyl group, we see those all the time. By definition, all three of those protons are always going to be equivalent. Okay, they're always going to be equivalent. Why? Because the carbon of a methyl is sp3 hybridized. Therefore, it's always going to have a sigma bond. It can rotate like this, and therefore all three of those protons are chemically equivalent. And then multiple protons, okay, are going to be chemically equivalent if they can be exchanged either through rotation or a mirror plane. Now here in this case, this is called 3-pentanone. We've got, not only do we have a plane of, or an axis of rotational symmetry, but we also have a mirror plane too. And so all four of those protons are going to be chemically equivalent. All four of them are in the exact same electronic environment. Okay, again, rotation works in this case, or a mirror plane works in this case, right? You can think about a mirror plane here, either way. but they're all going to be chemically equivalent. So you need to familiarize yourself with these 4 rules in order to determine how many signals are in an organic molecule. And if you go in the practice problems in our textbook, there's all kinds of great problems that help you identify, are these protons, homotopic, enantiotopic, diastereotopic, therefore are they chemically equivalent or non-chemically equivalent? And I told you that normally we run most NMR samples at room temperature. Okay, that's, I'd say, have 99.9% of NMR samples are run, but you can do variable temperature NMR. Now let me explain why you would want to change the temperature of your sample. If you were to run an NMR spectrum on cyclohexane, you guys all know that you can write just the 2D bond line structure of cyclohexane like that, but you also know that it exists as a chair where you have 6 protons that are axial and 6 protons that are equatorial. So technically, they're not in the same environment, are they? Right? All these protons that are in red are not in the same electronic environment as the ones in blue. I mean, these ones are axial, they're pointing up straight up. This one's pointing down, but it's equatorial, right? So they're not in the same electronic environment. However, if you run an NMR spectrum at room temperature on cyclohexane, all you see is one signal. Okay, you just see one signal. Now, why would that be? It's because we know that the ring flips back and forth, really quickly. Okay, and it's like the shutter speed of a camera, right? When the NMR instrument is taking a look or is, pulsing the sample with the frequencies of electromagnetic radiation, it's slower than the chair flip is happening, and so you actually get it, all the signals averaged out as one signal. Now, what would happen if you were to cool the sample to minus 100 degrees Celsius, which is really cold, okay? Then the ring flip is like, it's a lot slower. And so basically what that kind of does is, in a way, it speeds up the shutter speed, so then you would be able to observe 2 signals. Now, this is more of an FYI thing that would be maybe worth, like, what's covered on this slide and this slide would maybe be worth the value of 1 multiple choice question. I wouldn't even ask on your quiz, and I would not ask it on a final exam, okay? But it's just the idea that you can get the ring flip to occur slow enough that you could distinguish between axial and equatorial protons. But beyond 1 multiple choice question, I wouldn't go into much detail about that. To be honest, I haven't done a whole lot of variable temperature in my life. I've only needed to do it maybe half a dozen times in 20 years as an organic chemist, so it's not something that I've needed to do a lot, and it would probably depend on what type of research you're doing. All right, well, with that in mind, let's get into a practice problem finally. So it says here, for each of the following compounds, identify, determine whether the 2 protons in red are homotopic, enantiotopic, or diastereotopic. So if we look at the first one, is there an axis of rotational symmetry in this molecule? Could anybody answer that? Rotational symmetry? Rotational. Is there an axis of rotational symmetry, yes or no? Yeah, absolutely there is, right? If you spin this molecule around, this axis right here, you end up with the exact same molecule. And so the answer is yes. So if there's an axis of rotational symmetry, could anybody tell me, would these be homo, enantio, or diastereotopic? They're homotopic, exactly. So these protons are homotopic. Yes. There we go. So homotopic. The next one, there is no axis of rotational symmetry here, right? If I was to draw a line here, for example, and rotate that, I don't get the same thing, right? However, there is a plane of symmetry in here, right? If you were to slice the molecule right down the 3-membered ring, right, you can see that these 2 protons have reflectional symmetry. Now, if you're having difficulty with that, what could you do in that case? In that case, you could do this. You could redraw the molecule, the chlorine like this. You have 1 bond going back, and you have another bond going out in front. And then what you could do is you try the replacement test. So I'm going to copy this and paste it over here. Okay, so I'll put a deuterium here, a deuterium here, a hydrogen here, and a hydrogen here. So what am I doing? I've got a stereocenter in the molecule, and I'm basically just inverting that stereocenter. So the relationship between these two compounds is that they are enantiomers. Okay? And so the answer is these protons are enantiotopic. Enantiotopic. Okay? It might be helpful to make a model of this compound in order to see the plane of reflectional symmetry. But again, if you can't see it, just by looking at it in 2D, no big deal, because all you have to do is the replacement test, and you see that you end up with enantiomers. Could anybody tell me about the two protons in C? Would they be homotopic, enantiotopic, or diastereotopic? Could anybody answer that one with relative ease? Okay, I'm not saying that anything is easy in organic chemistry, but with relative ease. Yeah, they're diastereotopic. Yeah, I see that 2 students already answered me that they're diastereotopic. Now, how did the students know that so quickly? Like, I'm just learning this. I'm just trying to figure it out. Well, if we go back here into our shortcuts, we said that whenever you have 2 protons in a methylene and there's a chirality center in the molecule, that they are not chemically equivalent. So they would be diastereotopic in this case. And you can see that in this molecule, I have the methylene and I have a chiral center in the molecule. So those 2 protons are diastereotopic. Now, if you want to do the replacement test, do it. There's no crime in that. You're going to have enough time on your quiz that you'd be able to draw each diastereomer. So let's give it a try here. Doesn't take that long. Right? It just takes a little bit of patience. Right? That's what Guns N' Roses said. So I'm sure those guys don't know anything about organic chemistry, but they know about patience. So there you go. You can clearly see that we end up with a pair of diastereomers. And so these protons are what? They're diastereotopic. Okay, the thing I love about these kind of questions are that, if you think about chapter 5, when we studied stereochemistry, there was some questions in there that were pretty challenging, where we had to kind of manipulate a molecule in your mind. And I know that all students improve in their ability to do that as the semester progresses. But when you get into NMR and you're looking at a big molecule, like these examples aren't that crazy. But if you get into something that's a little bit more difficult and you're really unsure, what do? Just do the replacement test, man. And we didn't do it for the first one, but you can. There's nothing wrong with doing it. You just redraw the molecule. Okay, we could draw it like this, OCH. Oops, that didn't mean for that to happen. So you just redraw the molecule, put a couple of bonds here like that. Just move this a little bit. There we go. So we're going to copy it. I'll paste it over here. Come on. There we go. And if we just do the replacement test, so we have a hydrogen here, and we have a deuterium here and here. Right? It's the same compound, identical compound. So either way, so I kind of like this because there's such an easy out. The replacement test is so helpful with students. And what you'll find is that the more you practice, the better you'll get at it. You'll be able to recognize whether protons are chemically equivalent or not really quickly. Well, with all that in mind, let's try, this is question 15.5, comes straight out of our textbook. It says, identify the number of signals expected in the proton NMR spectrum of each of the following compounds. So I put a note in here for myself that you might want to look at Skill Builder 15.2. I think it's really well done, and it will help you to, determine how many unique protons there are in a molecule. But if we start with A, and I'm going to guide you through this one first, okay? I'm going to do A for you. If you look at A, there is no axis of rotational symmetry in this molecule, okay? If you cannot rotate this molecule. There is no axis of rotational symmetry in this molecule, none. So, but we know that these 2 protons on this methylene, the 2 protons that I have highlighted in yellow, could anybody tell me, are these chemically equivalent, yes or no? I'm not asking about whether they're homotopic and enantiotopic. I'm just or diastereotopic are they chemically equivalent? Yes or no? Based off of what we've learned so far. Could anybody answer that? So the answer is they are chemically equivalent. How do I know that? How do I know that they're chemically equivalent? They're chemically equivalent because I know that there is a CH2 here, okay, CH2, and there are no chiral centers in the molecule. Right? There's no chiral center anywhere in here. So by definition, these two protons are chemically equivalent. Okay? Why don't you guys work on this for a second, and I'm going to build a model of this. Just give me 2 shakes of the lamp's tail. Just going to quickly put together a model here for you. Demonstrate. Because a picture is worth 1,000 words. Well, a model should be worth even more, right? Just need to put oxygen here. All right. Ethyl group. 2 ethyl groups. Okay. Let's have an ethyl group here. Ethyl group over here. Okay. Okay, I'm going to switch over here for just a sec, just to show you the plane of symmetry, of reflectional symmetry. So I'm going to have to back up quite a bit. I'm going to try to make the background as conducive as I can. My office is really torn apart right now because I'm still working on painting it. But here's that molecule. Okay, here's the molecule. So we have the methoxy group up here, right? We have oxygen, CH3. We have the 6-membered ring. We have an ethyl group right here. Okay, there's CH2, CH3, and then there's CH2, CH3. So we were talking about these 2 protons here. Well, watch. If I rotate the molecule, you can clearly see that I get something different, right? This ethyl group is on this side, right? But then when I rotate it, there's no ethyl group here. So there's no axis of rotational symmetry. The axis of reflectional symmetry is like this, okay? If you look down the molecule like this, okay, and I mean straight down the molecule, yes, there is an axis of reflectional symmetry. Maybe I could hold it like this, okay? But you see how everything is reflected when you look straight down the molecule. For those 3-membered rings that we talked about a few minutes ago, it's the same thing. You have to look down it this way. And you see that these 2 protons on that ethyl group, they're reflecting each other, right? Okay, these 2 protons down here on this ethyl group, same thing, they're reflecting each other. Does that help a little bit? So this is what reflectional symmetry is. Okay, I'm just trying to adjust this to make it exact, but there you go. That's reflectional symmetry, my friends. Yeah, it does. Yeah, so Warren makes a good point. He said, I thought maybe the methoxy made a difference, right? But there's free rotation around this bond. Okay, so like this. Okay, so there you go, like that. Yeah. Does that help a little bit? Anyone? Hope so. All right, cool. Yeah, so you have to look at it sideways, right? And I mean, there's no such thing as sideways with a molecule.